Hello, a real brief presentation of what I'm up to here, just to get people excited. The idea is to create the octahedral stress surface, which is shown here, the top half of the structure. And it is based solely on a 19th century sort of two-dimensional layout, but now in 2019 we could do this parametrically and quite beautifully. I think that's probably no other word for it. So the idea is I'm using this kids program. It's called GeoGebra. It's to teach children geometry and algebra. That's the name of it. So given a stress matrix, which is known here, we can rapidly come up with the principal stresses. And I do that two ways in this example here. One is through the plotting of this function where the x's are, let me make the font a little bigger here. The x's are the stresses, and we're just looking for when the function zeroes out. So it's an eigen problem here. And it's a wave here, but it looks almost vertical because of the huge numbers. But where it crosses zero, that is the roots of the solution. That's one way of doing it. I didn't actually do that, though, to get these numbers. I actually used the second method, which is these small cofactors. It's breaking up the three-dimensional eigenproblem into a couple of 2D problems. It's all, I didn't invent it. It's straightforward. You get the three principal stresses, and from that you make three circles which are centered on the three different Moore's circles. So 1 to 2, 2 to 3, and then 1 to 3, the big one. Okay. For the octahedral stress, then, what we do is we draw 90 degrees on this diagram, which is 45 degrees in real life. And we intersect the first circle from C1 going straight up, and then from C3 going straight up to get B3. And then what we do is super cool. We draw these arcs, and I could do this with this parametric program. And what we're doing with one of the arcs is to start at 12 o'clock on this circle and go all the way to sigma 3. And we just do it with trial and error, just to kind of get the, until the end, this end hits the sigma 3. And we do that the same with the other one. We go from B3 to sigma 2. So all of the sigmas are covered. And where those lines intersect, that is the octahedral normal stress and the octahedral shear stress, i.e. at 45 degrees. But then what's super cool, I never knew this, that the square of the base of the top octahedra shows up on this plot too. And here's the 3D plot, which I think is super exciting to see how this looks. And I plotted all of the stresses, the actual stresses, the tau, the net shear stress, and the normal stress on that plane, and then I drew the four planes of the top octahedra. So I'd love to explore this a little bit more, maybe with some students, and kind of see how we could learn more from each other. Okay?